This week I will be talking about high resolution spectroscopy using laser light. I will talk about different methods which can be used to achieve spectroscopy with a resolution much higher than what was possible previously. In fact, since tuneable lasers have been developed back in the 1970s, various methods have been invented to take advantage of the high monochromaticity, long coherence time, and also the possibility to observe nonlinear effects related to the high intensity available with laser light. And so these techniques, one of them is called saturation spectroscopy. The other one is called two-photon spectroscopy, have allowed to reach a very high resolution, as we will see. What was the main limitation to the resolution before lasers? It was the Doppler effect, the fact that if you shine light on a sample of atoms which are moving in all directions, the atoms see in the reference frame a frequency which is different from the laser frequency. If they fly towards the laser, they see a frequency which is increased. If they go, there is an echo here, I don't know what's going on. If they go against the laser beam, the frequency is increased. If they go in the same direction as the laser beam, the frequency they see in their frame is diminished. And since you have all kinds of velocities in the sample, this results in a broadening of the line, which washes out all the structures, fine structure, hyperfine structures that one wants to measure. And so we'll see that saturation spectroscopy and two-photon spectroscopy make it possible to get rid of these effects. Now, the most radical way to get rid of the Doppler effect is, of course, to stop the atoms. So if you can work with samples in which the atoms do not move or have a minimum motion, the minimal motion which is compatible with Heisenberg uncertainty relation, then you have another very drastic way to get rid of the Doppler effect. And I will describe experiments in which this is achieved with trapped ions. We'll see that lasers can be used to manipulate the ions, to do very precise spectroscopy with them, and also to use the ions as qubits in quantum information processing by coupling two ions using laser light. Finally, I will talk in more general terms about quantum interference phenomena. We'll see that in these manipulations, usually we make use of the fact that you can put the system in a superposition of states and take advantage of quantum interferences, and I will give you a few examples to conclude the lecture. So let's start with high resolution spectroscopy, and of course for that you need tunable lasers. Historically, the first laser which made this possible was a dye laser, optically pumped dye laser, which was invented in the 1970s by Hänsch. You see the dye molecule has a ground state, ground level with many states differing by the rotation vibration of the molecule, and an excited state here. And using a UV pump, you can bring the molecules from the ground state to an excited state here. Then they decay to the bottom of the excited band by non-radiative processes, collisions, relaxation between vibration and rotation motions. And so you get a population inversion between this state and a lot of states in the ground state here. And so the system is able to laze on a very wide range of frequencies. So these are dye lasers. They're usually pumped, at that time they were pumped by pulse nitrogen laser in the UV. You see here a picture of the first setup, and here a sketch which shows how the laser was arranged. You see that this nitrogen pulse signal is focused on the cell in which the dye is being circulated. The dye is usually solved in ethanol or methanol. And so the dye molecules fluoresce. This is in a cavity which is closed here by a mirror and at the top by a grating. The grating is inclined at an angle, and the grating acts as a mirror which filters one wavelength depending upon the orientation of the grating. The light which is reflected back in the cavity has a wavelength which can be tuned by changing this angle. Here you have a telescope made of two lenses whose role is to expand the beam on the grating so that the light illuminates more grooves of the grating and you get a higher resolution. And in order to still increase the resolution, Ted Hänsch introduced here a Fabry-Perot étalon. In fact, it's a very thin blade which acts as a colored thin plate, which reflects, which transmits specific colors depending upon the separation between the two faces of the blade and its orientation. So by tuning synchronously the grating and the étalon, you get a very narrow output. By very narrow, I mean at that time it was narrow. We will see that a lot of improvement have been obtained since then. This was a pulsed laser because the nitrogen pump was pulsing the excitation. And so the bandwidth was ultimately limited by the inverse of the time of the pulses. So it gave a very limited resolution, but still it allowed to do a lot of interesting experiments. Just to give you an idea of the progress which has been made during the last 60 years, I show you here what was the best source of monochromatic light before the lasers. This is a krypton lamp. So you have here a krypton in a cell. An electric discharge excites the krypton atoms and they emit lines. And you see here a red line. This red line was the standard of length before the lasers. In fact, the meter was defined as a multiple of the wavelengths of this laser. So this red line was used in an interferometric Michelson apparatus to measure the meter. What were the orders of magnitude? The frequency is about 5 times 10 to the 14, but the width of the transition was about 1 gigahertz because of the Doppler effect, because the krypton atoms in the lamp were moving in all directions. So you see that the quality factor, delta nu over nu, is only 1 part in 10 to the 6. Another way to look at this is to say that it's possible to see an interference when the difference in the path lenses is about 10 to the 6 wavelengths. 10 to the 6 wavelengths is about 1 meter. So the best classical interferometers could work with a path difference of about 1 meter, and so we could define the meter in this way. Now, 60 years have passed, and I show you here the best lasers we have today. I will discuss them more in the following lectures. These are the lasers which are now used in atomic optical clocks. You see here the line width. When you scan the laser width, you have a width which is now 0.25 hertz as compared to the 10 to the 9 hertz that you had before. This means now that delta nu over nu is 6 parts in 10 to the 16. And the coherence lenses are 1 billion meters, 10 to the 16 wavelengths of light. 1 billion meters, that's more than the distance from the Earth to the Moon and back. This means that if you could build a Michelson with 1 mirror on Earth and another mirror on the Moon, the return light could interfere without skipping a bit of the light over these huge distances. In fact, the lasers which are being used in the gravitational antennas, which have observed a burst of gravitational waves, are lasers of this kind, which are very, very stable and which allow to do interferometry with a huge precision because of the coherence of the laser light. So I will say more about the way these lasers are stabilized. I will be talking about optical clocks in a couple of weeks. But I just wanted to give you an idea of the huge progresses which have been made with light sources when you go from the best classical lamp, which could be used in the 1960s, and the best lasers that we can use today. So let's talk now about the Doppler effect, and I will go rather fast because I hope that you know about this, at least classically. You see here a wave which is propagating from left to right, and assume that you have an atom moving in the direction of the wave with a velocity VA. In the reference frame of the atom, the phase of the light is just k z of t, where z of t is the law which describes the motion, minus omega t. And when you develop this, you find very easily that you have, in fact, an apparent frequency in the reference frame of the atom, which is omega minus kVA, where k, which is equal to omega over c, is the wave vector of the light beam. So we retrieve here the fact that I indicated qualitatively that in the moving frame, the frequency of the light appears reduced in this case, and of course it will be increased if the atom was going in the opposite direction. Now, V over C usually for atoms at room temperature is of the order of 10 minus 6, 300 meter per second compared to the 300,000 kilometer per second of light, which means that delta nu is of the order of 10 minus 6 times the frequency, which is of the order of the gigahertz for optical transitions. Now, let's look at how you describe this effect when you discuss the exchange between atoms and light in terms of photons. And so I show you here this interpretation in terms of photon. I consider the emission process. I assume that I have an excited atom whose internal energy E sub E. It emits a photon and falls in the ground state with energy E sub G. And it emits a photon of frequency omega, that is energy h bar omega, and momentum h bar omega over c. The initial momentum of the atom is p z, and the final one is p prime z. And I assume just for simplicity motion in one direction. So I write here the conservation of momentum. It's non-relativistic. I just assume very small velocities. So you take the non-relativistic momentum, and pz is equal to p prime z plus h bar omega over c. So the momentum of the atom plus the momentum of the photon. And the conservation of energy requires that pc squared over 2m plus sec, the internal energy of the atom plus its kinetic energy in the initial state, is equal to the same quantity in the final state plus the energy of the photon. You can use the first equation to eliminate p prime z, and you get the conservation of energy here, which is a simple equation that you can solve. And when you solve this equation, you find again the Doppler effect, omega minus omega Eg. This is the difference between the energy of the frequency of the laser and the frequency of the atomic transition. It is equal to VA over C time omega. This is a Doppler shift, which is the same as above. But you have an extra term here, minus h bar omega squared over 2mc squared. This is called the recoil energy. The recoil is something that you can understand easily. Assume that the atom is at rest. When it emits a photon, it recoils because momentum has to be conserved. So, and if it recoils, it means that part of the energy of the atom goes into this recoil energy, which means that the energy of the photon has to be reduced. H bar omega has to be reduced by this recoil to conserve the energy. And this is what this minus term is here. Now, let's look at orders of magnitude. The recoil is h bar omega times h bar omega over mc squared. So you see that the recoil is in fact very small. It is the energy of a light, of a photon, multiplied by the ratio between the photon energy and the atom rest mass energy mc squared. Now, the orders of magnitude are very easy to evaluate. H bar omega is of the order of 1 electron volt, that's the energy of an atomic transition, and mc squared is of the order of tens of giga electron volt, that's the mass, rest mass of atoms. The ratio is about 10 minus 10, 10 minus 11, so it's a very small effect. But it's still an effect which we have to take into account in high resolution spectroscopy. Moreover, you see that the effect, and we will see it in a moment, takes an opposite sign, whether it's in absorption or in emission. This means that if you have enough resolution, you will see this as a doublet. Each atomic line will have one frequency for emission and one frequency for absorption, which are slightly different because of this recoil effect. And in fact, this recoil is very important in Moss-Bauer effect. If you replace optical transition by nuclear transitions, you see that h bar omega will become much bigger, and the recoil effect will become much bigger. And this explains that if you have nuclei which emit gamma rays, the frequency of emission is different from the frequency of absorption. So if the atoms are flying in a gas, you will not be able to use a source of emitting atoms to get them absorbed in another sample. On the other hand, if these atoms, these nuclei are embedded in a crystal, then the recoil is taken not by individual atoms, by the whole crystal, and then the absorption and emission line coincide. This is called the Mossbauer effect. We already alluded to it when we talked about the measurement of the gravitational shift. It's something which is important in nuclear physics, and we will come back to this later. But what I want to say here is that the Doppler effect and the recoil effect are the two main effects which affect the position of light due to the motion of the atoms. There is a third effect, which I did not discuss yet, which is called the second order Doppler effect, which is in V square over C square. And I did not find it here because I used a non-relativistic equation. But if you use relativity, what you find is that you have this second order Doppler shift, whose physical explanation is very simple. It's just the fact that the clocks in the atomic frame run slower because of the time dilation effect of special relativity. And this effect is of the order of V square over C square. So for thermal atom, it's 1 part in 10 to the 12, which is exceedingly small, but still measurable. Now, if you use cold atoms, then it becomes 1 part in 10 to the 20, because V square over C square becomes very, very small. And in modern atomic clocks, we still have to take it into account, but it's barely visible because 10 minus 20 is a very small perturbation. So just on this slide, I give a kind of synthetic view of what I just said before. I represent here the energy of the atom in the ground state. So I call the origin of energy here Eg. And this parabola represents how the energy, the kinetic energies varies with momentum in one direction. In the excited state, you have the same parabola, which is just translated by the energy of the atomic transition. Now, let's look, for example, at the absorption process. You start with an atom which has a given velocity, and the atom absorbs a photon. So it takes the momentum of the photon, and the momentum of the photon is just increasing its momentum, and it brings it to this point. And you see immediately the slope of this line here is just the velocity of light, because it's a ratio between h bar omega and h bar omega over c. But you see from this graph that the energy of the transition is larger than that h bar omega has to be larger than h bar omega Eg. On the other hand, if the atom is, instead of absorbing, is emitting, it's going down. And again, you have these schematics here, and you find again a shift between the frequency of the photon and the frequency of the atomic transition. Now, on this graph, you don't see the recoil effect because it's a second order effect. So I just show the recoil effect here. I assume, if you assume that the atom is initially at rest, you see that if it absorbs a photon, it has to recoil. So it gets a momentum, and you see immediately that the energy that the atom has to take in is larger by delta A recoil than the just atomic energy. So it explains that in absorption, the photon has to be a little bit more energetic. On the other hand, if you emit a photon, you follow this line, and you see now that you need a photon which has an energy slightly smaller than the transition energy. And this is a plus, minus, or plus sign of h bar omega over 2mc squared I was talking to you about. So you see on this diagram, you understand well how the Doppler effect is related to the conservation of energy and momentum between atom and light. So how do you get rid of this? First of all, what is the effect of this on atomic transition? And I have chosen here the simplest possible atomic transition in hydrogen. And I'm looking at the transition between the n equal 2 and n equal 3 state in hydrogen. This is called the Balmer line in the red part of the spectrum. You see here in n equal 2, and we studied that when I talked about the time shift. In n equal 2, the angular momentum can take the values L equals 0, this is the S state, or L equal 1, these are the P states, which have two fine structure states, 1/2 and 3/2. And this frequency difference, this gap here, is called the fine structure of the first excited state of hydrogen. And to give you the scale, this is about 10 gigahertz. Then you have, again, the structure in the n equals 3 level. N equals 3 now has L equals 0, S state, L equals 1, P state, and L equals D, L equals 2, D states. And when you connect the n equals 3 manifold to the n equals 2 manifold, you find essentially 7 lines, which I've shown you here, which are the transition between these states. And before the lasers, so you see all these lines, they are somewhere here in the red Balmer line here. When you do experiments with a sample in which the atoms are going all directions, what you find is something like that. You find 2 bumps separated by about 10 gigahertz. So this is just an indication of the fine structure here. But all of the fine structure components corresponding to n equals 3 are buried. There's these lines which are buried in this big structure. So you don't see anything, even if the hydrogen atoms are at a reasonably low temperature because of the Doppler effect. And in hydrogen, the Doppler effect is very big because hydrogen is light, and so its thermal velocity is large. So how do you get rid of that? And I first will describe one method, which is called saturated absorption spectroscopy. So what we do in this method is to submit the atoms to 2 counter-propagating light beams of the same frequency. So we just take one light beam, we split it into 2, and we send the 2 beams in opposite directions, in a kind of standing wave configuration. So let's look first at an atom which is moving from left to right. What is the condition of resonance for this atom with the beam going from left to right? We just get, it's very simple, you find that the velocity of this atom has to be equal to c times delta omega over omega, where delta omega is omega minus omega Eg. This is again the Doppler effect. Now, what is for the same atom going from left to right, what is the resonance condition for the counter-propagating beam here? You get a very simple expression, and now you find that VA has to be equal to minus C delta omega over omega. So you see that for an atom moving with a non-zero velocity, this atom will see the 2 beams with different apparent frequencies. So what will be the effect of that? I show you what I have represented here is the velocity distribution, the Maxwell velocity distribution along the direction of the laser beam. So the most probable velocity is 0, and then it decreases according to a kind of bell-shaped curve. This is the usual Maxwell distribution. Assume that the beam going from right to left is very intense. I call it the pumping beam, while the beam going from left to right is a probe beam, which is rather weak. What will happen? You see, because of this condition, that the pumping beam going from right to left will decrease the population difference by a large effect. It will just have a tendency to equalize the population of the 2 states. So it will decrease the population difference, decrease the number of atoms in the ground state, and increase the number of atoms in the excited state. In other words, what we say is that it burns a hole in the velocity distribution. On the other hand, the weak beam going from left to right sees the mirror velocity class, and there is a small effect due to this saturation. So you see that as long as omega is different, delta omega is different from 0, the 2 beams interact with different atoms. And so if you sweep delta omega, the effect on the weak beam absorption will be independent of what happens on the strong beam, unless you get at delta omega equals 0. So you see that the absorption of the weak beam is independent of the strong beam, except when the frequency of the laser coincides with the frequency of the atomic transition. And what happens in this case, then these 2 holes are merging, and you see now that the weak beam will be less absorbed because there will be less atoms in the ground state due to the strong beam. So there is a decrease of absorption of the weak beam at the center of the Doppler of the Maxwell velocity distribution. This reflects in this way. It means that if you tune the frequency of the laser, at the center, when delta omega is equal to 0, you get a dip in the absorption profile. And this dip has a width which is a natural width of the excited state, no longer the Doppler width. And usually the natural width is about 3 or 4 orders of magnitude smaller than the Doppler width. So you get a very narrow dip in the center. This is called, and again, we find the same people again and again. This is called the Lamb dip because it was this phenomenon was predicted by Lamb, who wrote the first quantum theory of the laser at the beginning of the 1960s. So you get this dip, and this dip is sensitive to fine structure effects because the Doppler effect has been eliminated. And this is the effect that Ted Hänsch used for his first measurement of the optical Balmer line. So I show you here the setup that Hänsch used. You have a dye laser. You split the dye laser into 2 beams using a beam splitter here. One beam is going from left to right. This is the pump beam. This is actually the probe beam. And one beam is going from right to left, the intense beam. This is the pump beam. And they overlap in the cell where you have hydrogen atoms. An electric discharge prepares the atom in the 2s state. And these beams are doing the spectroscopy. So you see, this is what was obtained before. And this is a kind of line which Hänsch saw with his very primitive tuneable dye laser. So in order to eliminate this broad background, the trick which was used here was to add a shopping wheel, a wheel which was interrupting periodically the pump beam. And the electronic detection was making the subtraction of the signal with and without this pump beam. So the subtraction subtracted the Doppler, the broad Doppler profile, and left only the very narrow peaks here. You see, for instance, here, this is about 1 gigahertz. This is a Lamb shift. These 2 lines, the distance between the 2s and 2p state here is a Lamb shift. And for the first time, Hänsch and Schawlow could see the Lamb shift on an optical transition. I remind you that 2 weeks ago, I described how the Lamb shift was measured for the first time. And in fact, it was a microwave experiment between these 2 states. But now it's an optical experiment. And you see a surprise that you have some extra lines. This peak here does not correspond to any line in the spectrum of hydrogen. So this is called a crossover signal. And on the next slide, I give you an interpretation of the crossover signal. It is due to the fact that, in fact, we're not working with 2-level system. Consider what happens if you have 1 ground state and 2 excited states. You see immediately that the population of the ground state is depleted by the pump beam when it is resonant with the G to E1 transition, for instance. So you just write that this is for atoms whose velocity is given by this expression. And the same atoms will be resonant with the probe field on the other transition, provided this condition is fulfilled now. You see, I have changed the sign from minus to plus because these are counter-propagating beams. And when you equalize these 2 expressions, what you find is that for this velocity, when omega is the average of omega G1 and omega G2, just for the frequency which is just at midpoint between these 2, the pump and the probe interact with the same class of atoms on one transition for one and the other for the other. So they speak to each other through this, in this class, in the same class of atoms, and you get an extra signal due to that. This crossover, so we have to understand that when you exploit the spectrum, you have to be sure that you know where are the crossover lines. So you see the average between this frequency and that frequency give you this signal here, which is not a real resonance, but which is due to this crossover. But still, the important point is that you get now a much higher resolution. Another technique has been developed a few years later, again, in particular developed in the group of Hänsch, but It was predicted before by people like Cagnac, Grynberg, and Chebotaiev in Soviet Union. It is the 2-photon absorption without Doppler effect. It's the same configuration as the one I considered before, 2 counter-propagating beams. But now, instead of absorbing just 1 photon, because of nonlinearities, if the laser is intense enough, it will be able to absorb 2 photons and to go directly, for instance, from 1s to 2s, each photon having exactly half the energy required to bridge the gap between the 2 levels. So it's a 2-photon transition. And I showed you in previous lectures that they had already been observed in the microwave domain, this kind of transition, but it was, of course, much harder to see them in the optical domain. But you see what happens if you absorb 1 photon of this beam and 1 photon from the other beam. The momentum transfer cancels because the absorption of the first photon increases the momentum of the atom, and the second photon decreases it by exactly the same amount. And you see now that if the velocity of the atom changes, you still have this condition, and you go for one parabola to the other one. So this 2-photon Doppler-free method cancels completely the Doppler effect and the recoil effect, and all the atoms contribute to the signal. In the saturation spectroscopy experiment, I remind you that, in fact, we were just seeing atoms whose velocity was perpendicular to the laser beams, the 0 velocity class. So saturation spectroscopy is selecting one sheet of atoms. And so in terms of signal to noise, it's not as good as the 2-photon spectroscopy, for which all the atoms contribute to the signal, whatever the velocity is. And what happens in this case, the only velocity-dependent shift is the second-order Doppler effect, that is the relativistic effect, the fact that the clocks in the reference frame of the atoms are different from what they are in a rest frame at rest in the lab. On the next slide, I show you the kind of signal you get when you do 2-photon spectroscopy. You get a very wide pedestal. Why? Because you cannot prevent the atom from absorbing 2 photons propagating in the same direction. And in this case, you have a Doppler effect. But when they absorb 1 photon in each beam, there is a very narrow center here. And it has been already also tested first on hydrogen, this time on the 1s to 2s transition. This is a transition from the ground state to the first excited state. It's called the Lyman alpha line, and it's in the far UV. So it's about 1,200 nanometer, 120 nanometer, excuse me. And so what you need is a photon whose wavelength is twice as big, 243 nanometer, which is still UV. And in fact, these 243 nanometers are obtained by doubling the frequency of a laser at the frequency of 486 nanometer, which is a blue-green laser. So you start from a visible laser, you double its frequency, and with the double photons, you make a 2-photon absorption. And the selection rule is such that you can make the transition from f equals 0 to f equals 0 in the 2s state, or from f equals 1 to f equals 1 in the excited state. And the structure you see here is a hyperfine structure, the structure which is due to the coupling of the electron spin with the nuclear spin of the proton. And you see here the first spectrum obtained by Hänsch. So this is about 1 gigahertz. In fact, the fine structure is 1.4 gigahertz in the ground state. So you see half of it, 700 megahertz, because you have 2 photons. And you see that the lines were rather broad because you're using pulse laser, which didn't have very good resolution. This was in 1974. And you see the hyperfine structure here. Then the progress has been, again, very big. 20 years later, instead of 1 gigahertz, you have here 100 kilohertz. And you see the line is now about 20 or 30 kilohertz. At this scale, the other fine hyperfine structure line is kilometers away. You cannot see it because the resolution is so big. And then again, something like 10 years later, here a width of about 500 Hertz. And you have now a very narrow line, two-photon transition line here. On the next slide, I give you a small description of the experiment, which is a tour de force. You see here the schematics, which shows that you absorb one photon going from left to right, one photon going from right to left, and you go from 1s to 2s. Now the 2s state cannot decay by one photon because of the selection rule. So the 2s state is very long-lived. In fact, it has a lifetime of about 0.1 second. So it's very long-lived at the atomic scale. And if you want to see a signal, what you have to do is to admix the 2s state with a 2p state. Because the 2p state, which is very close, is the Lamb shift effect. 2p state has a short lifetime. The 2p state can immediately decay by one photon emission down to the ground state. So the way the experiment is done is here. You have hydrogen, a beam of hydrogen atom. The molecules are decomposed by a electric discharge, and the atoms are merging into a beam going horizontally over a distance of about 1 meter in an evacuated tube. And here you have the two mirrors, which make a cavity, and you have a standing wave, which is a wave producing this field, going back and forth inside this cavity. Here you have a finger which is cooled at the liquid helium temperature, because we want to have cold hydrogen in order to decrease the Doppler, to decrease the velocity of the atoms and the second order Doppler shift. So in fact, you have atoms which go rather slowly and which propagate along the beam while they interact with the two counter-propagating laser beams. When they reach the detection zone here, they are submitted to an electric field which mixes 2s with 2p. So it immediately quenches the 2p state, which decays, emitting a Lyman alpha photon, which is detected by this photodetector. So the signal is the 2p emission, 2p to 1s emission, which occurs only when the resonance condition is achieved when 1s has been promoted to 2s. You have another trick here. You have a chopper here which interrupts the laser beam. What is the use of this chopper? This chopper allows you to find out exactly when the atoms start to be excited here, when the light is coming back. And then the detection is delayed by a time corresponding to the time of flight of the atom from here to here. And if you increase the delay between the chopping and the detection, you will detect slower and slower atoms. You let the fast atom go by, and you detect only the atoms which are slow enough to fall into the window between the excitation and the detection. This is a trick which allows, without cooling the beam below a few hundred meters per second, to detect only the tail of slow atoms in order to decrease the second order Doppler effect. And so you have a lot of tricks which are being used. And it is with these tricks that you get this very, very narrow line, less than 1 kilohertz on a UV transition. I remind you that the lifetime here is about 1 second, so 1/10 of a second. So in fact, the natural width here should be only 1 hertz. So there is still a lot of orders of magnitude to win to increase still the resolution. But let's stay with this and conclude this part. On this diagram, I show you the progress which has been made in optical spectroscopy of hydrogen over 1 century. The first experiment started before the lasers, and at that time, the progress was rather slow. You see here, it's in power of 10. You reach a precision of about 1 part in 10 to the 7, something like that. Then the laser came, so you had the first generation of lasers here, which increased the resolution by a large amount. And now you have a second step here, which started when it became possible to measure directly the frequency of optical transition. This will be the topic of a lecture I will be giving in 2 weeks or 3 weeks from now, but I just want to give you orders of magnitude now. What is the frequency of the 1s, 2s transition? You see it's given now with 14 significant digits. This is 2×10 to the 15 hertz with this huge precision within plus or minus 10 hertz in the end. So it gives you an idea of the precision we can reach now, because we can do this very precise experiment with these very stable lasers and measure the frequency of the transition. You can also extract from this the Grynberg constant, which is given with a somewhat reduced precision. Why R is less well known than the frequency? It's because in the Grynberg, you have the mass of the proton which enters into play, and the precision with which the mass of the proton is known is not as good as the measurement of the frequency. But still, you have 12, 6, 10 minus 12 here on delta R over R. Another very critical number is the lamp shift of the ground state. I remind you that the first lamp experiment was able to measure the lamp shift between 2s and 2p because the 2p state was used as a reference, and it was about 1 gigahertz. But what the theory showed is that the ground state has a lamp shift 8 times larger, so it's about 8 gigahertz instead of 1, but it could not be measured before lasers because there was no reference. But now, if you can measure the 1s to 2s transition with a high precision, you can find what is the contribution of the lamp shift. And this is the precision of the lamp shift now. You see it's known now with 6 figures in the ground state. This is a very, very stringent test of quantum electrodynamics. What I want to say in conclusion is that in order to achieve this level of precision, narrow optical lines are not enough. One must be able to count directly optical frequencies. And this happened because of the invention, again by Ted Hänsch and colleagues, of the frequency comb lasers, which have revolutionized the measurements of time. And I will talk about this technology and the achievement in lecture 12. I would like to finish this part of the lecture by coming back to a point that I mentioned before without giving any experiment, without describing any experiment so far, which is the recoil shift. I told you that the recoil shift is about 1 part in the 10, 1 part in the 11, and it gives rise to a doublet. And this is the first observation of the recoil shift. It was made in 1976, and it was made at a time when tunable lasers were not so common, and the spectroscopy relied on coincidences. And I remind you that I mentioned in the last lecture that there was a famous coincidence between a line of the helium neon laser at 3.39 micrometer and a transition in methane, CH4, and this is a coincidence which was exploited here. You see here the methane line, which is being scanned by a helium neon laser. These are rotation vibration levels. And you see each line has a doublet, small doublet. And if you take the derivative of the signal, in the derivative of the signal, you get a stronger structure in the middle, which reveals this doublet. So it was the first observation in the optical domain of the recoil effect. I remind you that, in fact, since it's a saturation spectroscopy experiment, it is sensitive to light going in both directions. And so you have, in absorption and emission, you have opposite sign for the effect. So you have a doublet for each line. What is the order of magnitude? I remind you this expression here. And so we have to compute it in the case of methane. The frequency of methane is 8.85 10 to the 13 hertz. And if you translate it into energy, it's 0.365 electron volt. And the mass of CH4 gives you an energy equivalent of 15 GeV. So the ratio of the two is 1.2 10 minus 11. And so delta nu recoil is about 1 kilohertz. And so the splitting is about 2 kilohertz. This is the splitting you see here. It's a splitting of 2 kilohertz on a line which occurs at 88 terahertz. And I mentioned this because historically, this measurement was the ultimate measurement of the velocity of light. And since this course is devoted to the history of light, and I talked to you in the first lecture about light, the velocity of light was measured back in the 17th century with a precision of about 30%, and then by Fizeau and Foucault in the 19th century with a precision of about 1%. Here I am talking about the experiment which will measure the velocity of light with a precision of 1 part in 10 to the 9. That is an improvement by 6 or 7 orders of magnitude over the measurement by Foucault and Fizeau in the 19th century. So what John Hall and his colleagues did was to measure at the same time the frequency of this line and the wavelengths corresponding to this line. And if you multiply the wavelengths by the frequency, you get the velocity of light. So of course, the big challenge was to measure the frequency. And it was before the frequency combs. And at that time, back in the 1970s, the only way to measure the frequency of an optical transition was to build a chain, a very complex chain, which was bridging the gap between the microwaves, the cesium clock, and the optical frequency. And I give you here an example of this kind of chains. This is a frequency chain which was built in Germany at the PTB lab later in the 1990s. You start from a quartz oscillator. You take an harmonic of the quartz, you just relate it to a hydrogen maser of the cesium frequency clock, and then you start increasing the frequencies by taking harmonics which extend into the gigahertz range and into the hundreds of gigahertz range. Then you get frequencies which are high enough to get lasers, mostly CO2 lasers. And then in the end, you get into diode lasers and optical lasers. And at each step, when you multiply the frequency, you have to make a beating of the new frequency with the harmonics of the old one. And the bit note has to be measured with precision. And so you can, step by step, bridge the gap between the cesium clock and an optical line. This was the calcium line at 657 nanometer, a frequency of 410 to the 14 hertz compared to the 9 gigahertz here. So you have a multiplication of frequency by about a factor of 50,000. I show you this here because this is already a tour de force experiment. It relies on the locking of lasers, which are locked to one another in a huge room. And the people who did that spent their lives to build these devices. And within a couple of years, when Ted Hänsch and John Hall invented the frequency combs, all this became obsolete because this was able only to measure specific frequencies. One line, you just focused on one line of calcium or one line in methane, and you spent years to measure the frequency. Now, on a tabletop experiment with the frequency comb laser, you can do this measurement on any line at a cost which is much smaller, and they cost not only in money, but they cost in time, and it's really fantastic. But this was the state of the art back in the 1970s. And you see here, in fact, the chain of lasers, these are CO2 lasers on this table, which was used by John Hall and his colleagues in the measurement I was mentioning before. So it's the first NBS optical frequency chain. And they looked at the 3.39 micrometer line of CH4. They measured the wavelengths. So the wavelengths was measured by interferometry. What they did is they sent this in a Michelson. They counted the fringes for this line and then compared to the fringes of the krypton, of a krypton laser. The definition of the meter at that time was a multiple of the wavelengths of the krypton line. So they get lambda. Then they measured nu using the frequency, this chain of lasers, and they made the product of nu with lambda, and they get for the velocity of light this figure, 2,099,792 kilometers per second, 0.458 meter per second, 9 digits. And this 9-digit precision is just limited by the interferometric measurement. And in fact, the krypton lamp cannot give a better precision for lambda because of the Doppler effect in the krypton lamp. So when this measurement was achieved, it was the ultimate measurement of the velocity of light because the standard of length could not be known better. So the metrologists then decided to change their philosophy and to admit this as the value, exact value of the velocity of light, and to define the meter as a distance traveled by light in a fraction of a second, which is 1 over this velocity. And this was a way to relate the meter to the second being known as defined as a multiple of the period of a cesium clock. So this was the progress, and now we are something like 50 years later, and another revolution is coming because the second defined with the cesium clock is not good enough. And we have optical clocks which can define the second much better. And this will be the topic of what I will tell you in 2 weeks from now. But I think it's a good point to stop here, and we have a 10-minute break before the second part of the talk. Thank you.